Good morning. It's my great pleasure to introduce you Professor Edward Chang. Professor Edward Chang actually is our adjunct professor at CSE department, Computer Science and Engineering department. I know him for a long time already. He graduated from Stanford in EE with a PhD in 1999. And then afterward, he joined UCSB and as an assistant professor, and promoting to full professor faster than the speed of light in 7 years. So, and then afterwards, he basically went to Google to become the director of research there for more than 6 years. And now he is the VP of HTC Research and Innovation in Taiwan. So today, he's going to share with us his experience on this signal fusion and big data analytics. So let's welcome Professor Chang.
It's great to come back to UST. And in '99, when I finished my PhD, actually I interviewed the institution and got an offer to join with Gary. And I actually went to Santa Barbara instead. So let me just briefly introduce what I do at HTC. And then we get into signal fusion and the big data analytics. So I'm heading HTC research, and we have about 200 people, and we are located in Taipei primarily. Also, Beijing has a team, and Silicon Valley has a few people. We recruited from Google, Facebook, and Twitter, and they are essential for us to establish our cloud computing and big data infrastructure. And our key competencies, including hardware, of course. HTC, if we can manufacture in phone, we definitely has very good design capability, and also wearables and sensors. We can do those hardware design pretty well. And the software, we have capability to do image processing and algorithm development and mobile services. And today I'm going to talk about our recent advancements in big data. So start with the Internet of Things. This is definitely a big topic, and people are talking about these days. And there are so many different kinds of sensors, including healthcare sensors, smart city, smart home, transportation, and so on and so forth. And I'm not going to touch upon every single one of them today. And I'm going to just mention how we develop some infrastructures and try to take advantage of sensors and plug into big data and launch a few very interesting applications. Then end up talking about the futures of big data and the sensor fusion. So this is, we're trying to build something for the future. And the foundation is we got a lot of data from sensors. And sensor data is pretty much a lot of haystack. And you need to have advanced algorithms to try to mine intelligent data out of them. So big data analytics. And if we can get intelligence out of data, and hopefully we can develop killer apps to service users. So that was our vision to start it about 2.5 years ago at HTC. So today what I'm going to cover, I would cover like 3 sets of sensors and what we have done with those sensors. The first set of sensors is kind of motion sensors. And we use motion sensors to do context-aware computing. And we also launched a 360-degree panorama application on our phones, and which take advantage of sensor technology. The second set of sensors, health sensors. And this is going to be, for sure, a huge new initiative for all major companies in the world. And finally, I will conclude with the traditional camera sensors. And the first part will involve in sensor fusion technology. And the second part of the presentation will focus on big data analytics. And big data is not simply just putting a lot of data on the cloud and making a lot of computers working on those data. And there are lots of interesting subtleties. And today I'll be covering, for sure, traditional parallel algorithms to speed up computation. But there are other 2 or 3 issues. One is when you get big data, and let's say you train a classifier, because the training data set is extremely large, and likely your model file, when you build your classifier, the footprint will be also very large. And the consequence is the power consumption can be extremely high on your cell phone or mobile wearables. And the high power consumption is not acceptable. So therefore, although big data is a virtual, but the footprint has to be extremely small. There's a contradiction between the two, has to be addressed. And finally, in medical sensors, typically the data set we can obtain is extremely small. So we are talking about dealing with a small data problem. How do we combine small data labeled with big data technology to improving diagnosis accuracy? Okay, let's start with some sensors on the phone to be kind of warming up the audience. There are a lot of sensors on the phone. I'm not going to get into details, but let's look at two sets of sensors, motion sensors and some RF sensors, including GPS and Wi-Fi signal sensing. And based on these sensors, and we can go through a scenario, we can enable some interesting applications. And this particular example I started about 4 years ago back in Google. I called it Alice Shopping Land, contrast to Alice Wonderland. So Alice, lady would really love to shop, right? So Alice one day went to a shopping mall with his boyfriend, and they were extremely happy. At least Alice was extremely happy. But Mike was very unhappy. So they said, okay, let's wait. Let's register our location. Then Mike went off to a coffee shop to wait there. And Alice went off to do shopping. And then after just a few moments, Alice received a message. And she was wondering, wow, maybe Mike texted me. So he looked at the text. It was actually a coupon sent from a nearby store. So this is an example of context-aware computing. First of all, a nearby store knows Alice is present in the neighborhood. And the second thing is the nearby store probably knows Alice's intent, but she is not walking very fast in the shopping mall. She was probably wandering around. So she's in so-called shopping mode. And she probably bought cat food before, or she posted some cat pictures on Instagram. So therefore, she got this message. And this is hinting context-aware computing. So she was happy to got her cat food of the week and then redeemed the coupon and then did her payment, and the shopping is done. Then she went out to look for Mike. And thanks to the local location-based service, she was able to reunite with Mike. And now she can actually utilizing location-based service to find even more mysterious things happen to Mike in the last few moments. Okay. So this example illustrates context-aware computing, as I said. The context in this example includes location and intent. Intent, today I'm going to use a transportation mode classification as an example to illustrate this intent. And content including lots of things, a person's preferences or his or her behavior history, and social interaction relationship and interaction with other people. Those data could also be useful to doing context-aware computing. So let's look at location service first before we get into intent detection. Location service, as we know, GPS, Wi-Fi, one can give us outdoor localization, the other can give us indoor localization. However, traditional technology either may not be extremely accurate or GPS cannot detect indoor location accurately. And even GPS outdoor, the power consumption is an issue. So we are facing a couple of challenges. One is, of course, accuracy of the localization. The second is we have to reduce power consumption. So therefore, about 3-4 years ago, our team introduced this concept called SINS, X and INS. INS stands for Inertial Navigation Systems, including like compass, accelerometer, gyroscope, and maybe other motion sensing devices. And then based on those sensors, and in a few slides, I'm going to show you we can compute direction and the speed of movement. And those sensors have been used in navigation, aircraft, missile, guided missiles. So this is nothing new. But utilizing on cell phones could be extremely challenging. And I will touch upon some basic challenges in a few slides. And X can be a reliable external constraint. For example, suppose GPS can be a reliable external signal. Before I get into UCST and I get my auto location identified, then once I get into the building, INS can take over to try to find out exactly my displacement from the entrance of coming into a UST. And for the people who do not know what is a gyroscope, basically gyroscope measures rotation of an object. This is a traditional mechanical gyroscope. It's utilized in aircraft. Will give the aircraft XYZ or a rotation kind of angular momentum. From angular momentum, the XYZ rotation can be computed. And nowadays, because of man's device advancements, gyroscope, accelerometer, and so on and so forth, can be actually devised in a very, very small chip and implant on a cell phone, on small devices. So based on these devices, like gyroscope, based on gyroscope angular momentum, we can compute moving direction. And the accelerometer will give us acceleration. And based on acceleration, do the first integral will give us speed. The second integral will give us displacement. And so 3 integrals, we will be able to get direction, moving direction, and displacements from these sensors. The 3 integrals could be a big challenge because any small arrows coming from the signal, the arrow can accumulative magnify. And so we have to deal with those problems. But let's just look at some typical examples how these sensors have been used. So in aircraft navigation, between satellite signals or radar signals, if there's any signal lapse, an inertial navigation system can take over to smooth out the trajectory path. And let's use a driving vehicle as an analogy. So if before vehicle get into a tunnel, we know the location of vehicle by the GPS signal. And once a vehicle gets into a tunnel, the direction and the acceleration or the speed is really given by the steering wheel and the travel speed of the vehicle. So although in a tunnel, the vehicle cannot get GPS signal directly, but INS will be able to give it the displacement direction. So therefore, location still can be detected. And likewise, we can utilize INS on the phone to be able to detect our location. So even in the outdoor scenario, the GPS sensing, suppose we continuously try to do high sampling rate to get our GPS location. The power consumption is an issue. And we can reduce the sampling rate to communicate with the GPS satellites and thereby save a lot of power. And in between the GPS samples, and we can utilize INS to try to link the trajectories. So like I mentioned, there are quite a few challenges, and including, for example, zero drift of accelerometer. If you put an accelerometer or G sensor on the table without any movement, the reading is not zero, and the arrow has to be removed. And for a gyroscope, the rotation, angular rotation, if you rotate a gyroscope by 360 degrees, typically you wouldn't get 360, you will get more or less. And the sensitivity is also temperature dependent. So even you can calibrate a gyro under, let's say, 30-degree temperature. If the temperature drifts to other temperature measurements, the calibration has to be redone. And configuration is another issue. When the chips get implanted onto a cell phone because of alignment situation, or the cell phone can be dropped on the floor, and the calibration can also be affected. So like I mentioned, the arrow progressively magnified. So all this arrow has to be mitigated, otherwise reading accuracy cannot be very high. And because of the time constraint, and also because the audience may not be experts in these areas, I would just refer you to a paper probably listed in the end of the slides. If you're interested in the details, you can take a look. This problem can be solved by calibration continuously, and also by solving a model we call VEM, using energy rather than 3 integrals to try to compute moving direction of a device. Instead of doing 3 integrals to get moving direction and displacements, we try to harvest the energy of the phone. If we can get the energy direction of the phone, we will know the movement direction of the person. So many applications can take advantage of this location detection. So I was at Hong Kong airport and I couldn't find my places, and indoor localization could be extremely helpful. And the same set of sensors can be utilized to do intent detection. So this is an example we call transportation mode detection. We like to detect whether a person is stationary, walking, running, biking, or in any transportation vehicles. And by having those information, we will be able to know what, where, and when of a person. In other words, we would be able to know the context, even intent, whether the person is really walking very fast or wandering in the shopping mall, those kind of intent. Then we can apply applications on the data. But by building such a classifier, we face this big data challenge. So the slide here shows on the left-hand side, we have 3 sensors, and we collect data from the sensors. And we have lots of people help us collect signals. And once the signal has been collected, we have done calibration, fusion, and so on and so forth, and eventually applying support-vector machines to train a classifier. And the problem we face here is the big data issue. So this is a kind of transition into the discussion from signal processing into big data. And once we have the data processed and classifier built, then suppose, again, I'm in Hong Kong airport. And on the right-hand side, this is the location kind of map. We have the store information. And when a user is wandering around, based on the user's intent, real-time intent, and maybe a coupon can be sent to a user. For instance, if the time is around noontime, and if the person is walking in front of Burger King, and maybe Kentucky Fried Chicken can just issue this person a coupon to lure the user to another restaurant. So definitely e-commerce can be one application on this kind of data. So there are 2 resource issues, as I mentioned in the beginning. One is when we have large volume of training data, we need to have scalable algorithms to be able to process those big data in a timely fashion. The second challenge is power consumption. And power has to be small enough, otherwise, very quickly, the battery on your cell phone will run out. So let's look at the first problem, how to deal with big data in a cloud computing setting. And this was a work we did about 6 years ago at Google. And the problem was when we apply support-vector machines on, this is not really a huge set of training data, only 1 million data instances. But both the memory requirement and the computation time could be really, really high. So this problem could be mitigated by applying many computers at the same time to work on the training problem. But then the challenge is, how can we divide the data onto multiple computers so the computation can be done in parallel? So the division of the data need to be done in a fashion, and data do not have dependencies on different machines. And there are a couple of ways to do it. One is we can do a matrix vectorization. So for support-vector machines, the detail I don't have time to go through, but the key thing is we need to be able to solve a matrix inversion problem in the middle of the computation algorithm. And matrix inversion is very computation intensive. It's cubic with respect to number of instances in the matrix. So traditionally, to try to decompose this large matrix, there are 2 approaches. One is a precise decomposition. You look at the slides on the top, there are 3 precise, exact decomposition methods. Their computational cost is also cubic. So using a cubic decomposition method to try to speed up support-vector machine doesn't make sense because it's a cubic problem itself. So we employ a lower computational cost method to try to decompose the matrix. So we actually use incomplete Cholesky computation to try to make the matrix smaller. So this is an approximate matrix decomposition. Original matrix, suppose, is n by n. We like to decompose the matrix to be p multiplied by p. And if the p is substantially smaller than n, you get computational savings significantly. And empirical study shows us the p in this case can be smaller than the square root of n. So the decomposition here, if this is square root of n squared, so m times n, this is be n squared. So the following, we're going to show animation how the decomposition is performed. So we have a big data matrix here, and we like to be able to divide the matrix into small vectors and distribute to P machines. Every single machine would take care of a vector, and eventually we join the results together on one computer. So on those machines, we start with this n by n matrix, and then we approximate this n by n matrix become n times P matrix. And every vector is n in dimension, and we distribute the vectors to P machines. So every machine handles just one vector of n dimension. So this is in the sharding phase. We're sharding the data onto P machines. And then once after we have sharded the data onto P machine, computation can be performed. The matrix inversion could be done in each individual machines. Then eventually we have to get the data aggregated on the final machine and to form this P by P matrix. Since P is much smaller than n, and the memory requirement for storing the P by P matrix is much smaller. So this could be done effectively. So the pipeline shows us two things. One is when the computation is very intensive, we can always do a divide and conquer. However, when we divide the data onto multiple machines, we have to worry about dependencies between data. If we have strong dependency between data, synchronization between machines will introduce large I/O overhead and synchronization overhead, and thereby the computational speed up will be limited. So therefore, the division of data has to be done in an independent fashion. And the method we just illustrated to you was the precise division was very computation intensive. So we did this approximate method. Approximate method for machine learning task, it turned out to be okay because machine learning itself is an approximate process. So the result was still pretty competitive to the original method. And the figure here shows the speed up. When the data volume is about 200K, the speed up utilizing 50 machines, we can achieve 41 times speed up. And this is pretty good. But if you see, if we increase the number of machines, the speed up started to be saturated. And this is because the I/O becomes the dominant factor. Once you have individual machine computed the data had to be shipped to the final machine to aggregate together. The I/O could be a bottleneck over there. But the good thing is, once you increase the data further, the saturation point can be deferred because the computational scale becomes much larger. And therefore, more machines can be put into this parallel computational framework. And this slide here shows the bottlenecks. And the orange color shows the computational portion of the task. And we have purple and gray area shows overhead. And you can see the more machines you use, the overhead start to show up. And so therefore, all the big data algorithms, we have to worry about how to minimize I/O overhead or in general non-computational overhead. So therefore, the speed up wouldn't be hampered by the MDOS law. And later I will show you a slide illustrate all the critical machine learning infrastructures we have parallelized both in Google and at HTC. And some of them is actually open source on the internet. You can download and you can play with. And by having this algorithm being able to run on multiple machines, and we can process large volume of data in a very short period of time. So come back to this transportation mode detection. With the millions of instances we collected, if we run them on one single machine, it would take weeks. But with a few hundred machines, just within a few hours, we can get our classified trend. And the accuracy was actually not bad. For steel, the accuracy is 92%. For biking, it's lower because in Taipei, people not only do biking, but also they ride motorcycles. And the ambiguity between motorcycle and bike is kind of there. So, but the interesting thing is when it doesn't matter where your cell phone is carried, in a pocket or in a bag or in your hand, the classification accuracy is okay. And this is only done by having signals from inertial navigation systems. If we like to further improve the accuracy, for instance, we like to know whether a person is in a private vehicle or on a train, And secondary information can be helpful. For example, if we know the bus route, and you know precisely a bus has to stop at multiple locations. If driving a personal vehicle, you don't have to stop there. Then easily you can differentiate whether a person is on a bus or in the taxi. But just using the signals itself on the inertial navigation system, the accuracy is not really bad. And the next issue we have to address is the power consumption. So this project initially I was working on about 4 years ago back at Google. The power consumption was huge. Every cell phone's battery capacity today is about 200 milliamp. And at the time, if you utilizing CPU to handle inertial navigation signals, the power consumption could be about 100 mA, and that's not acceptable. So the problem has to be addressed by both hardware solution and software solution. So at HTC, because we are a hardware company, we can offload the computation from CPU to a sensor hub. On a sensor hub, we can employ a much lower capacity CPU, and therefore the power consumption is much, much lower. All the sensors will connect to the sensor hub, and once after the signals has been processed and fused, then the data sent to applications through CPU. And the power reduction is very significant. But in the software, we still need to address the problem I mentioned in a few slides ago. When support-vector machines apply to big data, the classifier, the footprint could be huge. If the footprint is huge, during the classification time, the computational time is still very, very long, and thereby the power consumption is very high. So in software, we still need to address that issue. So rather than getting into details at a high level, let me illustrate what happens here. So in support-vector machines, you can look at this classifier in two perspectives. One is in the original spatial domain. Basically, you have a number of features, and you want to, in the feature space, finding a hyperplane to divide different classes of data. And you also can look at the problem in a dual domain. In the dual domain, basically using support vectors to find the boundaries between training instances. So there are trade-offs here. Suppose you build a classifier in the dual domain. Then your computation time depends on number of support vectors. When we apply big data, the number of support vectors will be large. So therefore, in the dual domain to do classification, the time consumption will be very high. But however, if the feature space is not very large, you can convert your parameters from the dual space back into a primary space. And then you do classification based on your feature dimension. So in this particular example, rather than get into the math details, this illustrates the results. If we utilize an RBF kernel, which projects data in infinite dimension, and although we can achieve very high detection accuracy of transportation mode, more than 91%, but the power consumption in the classification situation is huge. This means in 2 hours, your battery will be out. But if we use polynomial kernel, the benefit is in the classification time, we still perform projection. But once the model has been trained, we can convert the model into the primary domain model. So basically using the original small number of features and learning the parameters, we can classify in a much faster speed. So this is the eventual result we used. We used the polynomial degree 3 in utilizing SVN in this particular setting. The power consumption is only 0.5 mA. So compare with a typical solution when I was performed back at Google, 88.5 mA. The solution we made, this is combined with sensor hub, also with this small footprint SVN. And the saving is more than 100 times. And probably you will argue 88.5 on a cell phone is not really deadly. But on wearables like your wristband or on watch, pretty much the power capacity is about 300 mA. And having 88 mA consumption cannot last the battery for too long. So this is a very important advancement. The details you can look into our VODB paper. Okay? So again, with such low-cost localization and intent detection in a shopping mall or in an airport situation, e-commerce application can be enabled. We also put into our cell phone so we can detect a person's movement. And on the left-hand side shows the panel of our product called FunFit. It displays a person number of steps taken during a day and the number of calories burned, the distance traveled, and so on and so forth. And this is very similar to like Fitbit and so on and so forth. And this can give everyone a sense of how much exercise has been performed. And you can compare with your friends on Facebook and doing a competition in real time. And the same technology also can be applied to camera technology. So let me just show you how we apply INS and put INS into the cell phone and to be able to support this we call panorama 360 degree. To capture 360 degree panorama is challenging because at the end you have to stitch two ends together. So most of the commercial products, they only support maybe 270 degree. But in the picture here we will give you the user the marker here. And user just follow the marker taking photos. And eventually all the individual photos will be stitched together. A 360 degree and 180 vertical can be constructed effectively. The reason, again, is because the inertial navigation system would detect the movement of the cell phone. So therefore, the stitching and also the ambiguity detection between nearby imageries can be done very effectively. So once the picture has been taken, you can go home to view the entire scene by just moving the camera. And again, this is done by inertial navigation system. You're moving the camera and the panorama can be displayed in front of you. Also, this is a tablet demo. It feels like you are in the original scene. And even more interestingly, you can take photos after you go home. So you utilize panorama to capture the entire scene. And at home, you try to view the scene using INS. And if you look at a particular angle, you say, well, I like to take a photo of that. And you can take a photo at home afterwards. So this was launched a year ago, purely based on the INS technology. Okay, so the next set of sensors I'm going to touch upon is health sensors. And why we get into health? About 2 years ago, and I was introduced by a group of professors from Harvard. They came to Taipei. They say, well, they would like to enter this big competition. This is the largest worldwide competition in medical devices. If you don't know S-Prize Foundation, probably you can go back to Google a little bit. S-Prize is a foundation to foster disruptive innovation. The foundation founders, including many big companies founders like Jeff Bezos and Bill Gates and so on and so forth, they donate prize money to foster disruptive innovation. About 12 years ago, they started the first competition was sending people to orbit to travel. About 7 years ago, the second big competition was self-driving vehicle. And lately, one very high-profile competition was lunar, I think, landing to the moon. This is a Google competition. So about 2 years ago, Qualcomm started a competition through the foundation, asked people to build a medical device, which is less than 5 pounds, will be able to do 15 different disease diagnoses and measure vital signs continuously. And this is quite challenging because traditional medical instruments to measure all these different diseases would weigh more than 100 pounds. And we entered the competition with another 255 entries about 2 years ago. And last year, we were announced to be in the top 10. And next month, we are going to ship the final device to UC San Diego to do final RRB. And the top prizes will be announced next year. The reason top prize will be announced next year is because the tricorder, the name, was coined based on this Star Trek Enterprise 2070. And you see Spark carries this tricorder. And he used this tricorder to do diagnosis of his colleagues on the Star Trek to see whether his colleague has any diseases or not. But in that fiction, he not only used the device to do medicine diagnosis, he also applied it to do curing. I think curing could be done maybe in 2070, but I think in the next few years, we only see a diagnosis can be effectively performed. And let's look at a list of diseases covered by the competition, and including imagery system, blood urine system, breath system, and vital signs. All this has to be packed into a very small device, less than 5 pounds. So today I'm not going to open up the box for you, but let's focus on one device and how big data could be applied, and what are the intricate in here to apply big data on this medical diagnosis scenario. So we look into this optical sense. And with a small camera, specialized camera, and you insert the camera into the ears, we can detect otitis media. So first of all, we insert the piece into a ear and taking a photo. And then based on certain training data, eventually we have to automatically saying whether a person has otitis media or not. So this process traditionally was done to collect clinic cases in a hospital and ask doctors to label the data, and then we can build a classifier to do classification. However, we face a different challenge. Let me go through this pipeline to illustrate what are the challenges. So suppose X denotes data, and the data can be divided into labeled data and unlabeled data. And traditionally, machine learning will apply an algorithm called phi, and whatever phi you pick imply the hypothesis on your classifier. Suppose vector machine or different kernels apply different kind of boundaries. And we apply phi onto either labeled data, sometimes combined with unlabeled data. We train a function f. Then this function applies to unlabeled data instances. We have predicted the outcome of this unlabeled data. And this is pretty much the pipeline of machine learning. And two issues we are facing. So big data for sure. I just illustrate for the SVM case. When the data volume is extremely large, and we have to do parallel computation, otherwise the time consumed is just not bearable. And I'm not going to get into details, but we have tutorial on the internet. We have done parallelization on these mission-critical machine learning algorithms, including SVM, frequent item set mining, LDA, and spectral clustering. And recently, Google also published a paper on deep learning parallelization. But today, I'm going to focus on a different problem on the big data. This is actually called small data. In the medical scenario, we don't have a lot of data. So our training data or labeled data is actually very, very scarce. The labeled data is very expensive to acquire. And even worse, even suppose a hospital can give me the labeled data. How am I, as a computer scientist, how do I know how to extract features from those data? So feature extraction relies on domain knowledge. Without domain knowledge, statistician or computer scientist, we just cannot do anything. And this is something we have done. So we collected about 1,200 instances from a local hospital about otitis media. And a year ago, we relied on hospital experts to teach us how to extract signals from those data. And we did build a classifier. Also, we published a paper together. The accuracy was about 80%. I will show you the accuracy comparison in a few slides. But then we said this is not good enough. This is definitely small data, and we are strongly constrained. So 3 months ago, we say, well, let's use totally a set of irrelevant data as the training data to see how we can apply transfer learning. And Professor Chang is an expert in transfer learning, so maybe he knows, he should have taught us how to do this before. And so we collected this 10 million ImageNet data set. ImageNet, if you don't know what it is, you can search on the net. These 10 million data instances have nothing to do with medicine. Those are data of daily objects, like vehicles, people, animals, and so on and so forth. And utilizing those objects, we apply the traditional encoding method. So this picture shows on the left-hand side, you have all this image data. We train a code book in the middle. It's just like you do compression. You train a code book. And eventually, you hopefully, when you do decompression, you can recover the original data back. So the unsupervised learning here, the mission is we apply the training here unsupervisedly, we get a trade code book. Hopefully, at the end, after we do decoding, we can get the original data back, okay? Encoding and decoding. The key message here is totally unsupervised, and the data has nothing to do with Untitled media. Then, once we have obtained the code book, we do the following encoding. So we obtain one Untitled media image. We say, okay, we get this code book, and how the code book can map our Untitled image into. So we get a sparse vector. And this vector will say, well, there are certain pivots in the code book may be able to depict this one Untitled media image. So basically, the original training image on this kind of encoding setting and getting pivots from this unsupervised learned code book. And we can have a combination of features representing each medical image. Then the medical image vectors, about 1,200 of them, because they have ground truth. And we using subvector machines to build classifier to do classification. And accuracy compared with the traditional approach we took last year. So here, last year initially, we use SVM, and based on the doctor's instruction, we extract features. And our detection accuracy was about 80%. Of course, this is including sensitivity and specificity. But look at combination of the two. Let's look at accuracy. It was 80%. So last year, we went back to the doctor. We said, well, the accuracy was not good. The doctor said, well, of course, when you insert the instrument into a ear, sometimes the direction may not be accurate. So you have to do segmentation to really get the inner ear out of the picture. So we spent another couple months to do segmentation, improving the accuracy to 85%. But the approach I just showed you was totally, nothing was done. There's no expert involved. We did not do expert-guided feature extraction. We didn't do segmentation. We just using this totally irrelevant set of internet photos with objects or vehicle, whatever, train a code book, and mapping medical images onto them. And the accuracy we achieve is almost 91%. This is really incredible. This is a very good example of transfer learning. Why this could have achieved, and right now we can only speculate, and our engineer is trying to reverse engineering this whole pipeline to see, in fact, what features were extracted out of those code book. But let's just review our visual pathway. Our visual pathway started with primary visual cortex sensing pixels into our eyes. Then, of course, there will be additional advanced processing in the back end. And if you know neuroscience, it will be V1, V2, and many layers. So the first layer is very fundamental, pretty much doing edge detection. And the subsequent layer may be doing parts forming, then eventually doing object detection. So what transfer learning performed here was perhaps help us a lot in this V1 stage, getting all the fundamental features from a set of 10 million photos and give us the code book, give us the foundation. So if we look at the deep learning pipeline, the first few stages could be totally unsupervised. And then we can map the target semantic in the final stages to perform or achieve this transfer learning. And this is another example. So basically, the idea here is we got fundamental features from the photos. And using those as a code book, then the kind of encoding medical image and extracting features out of the code book and do a high-level supervised learning. The result is quite interesting here. And then we apply the same technologies to try to do classification between animals like dogs and the cats, or even detecting different breeds of dogs. And there was an experiment we performed to detect or classify 120 different breeds of dogs. And the accuracy we could achieve was about 80%. So the technology encouraged us, even in the medical domain, we typically cannot get a large set of training instances. But through this transfer learning idea, we can still achieve very high accuracy. And finally, because the slide is not moving, let me reboot the machine at the same time So the final set of slides was trying to show, once we have get this technology, we can do object detection. This set of technology can apply to image annotation. Every image, objects, and the semantics or labels can be harvested by going through this unsupervised training pipeline, plus eventually supervised learning. And then we develop a product called One Gallery. And regardless where you have uploaded your photos may be uploaded to G Drive or a Dropbox. We index all your photos together back onto your cell phone. And utilizing all the metadata we have collected, we can support image retrieval. We can support very effective browsing experience. So to try to move to concluding today's talk. So basically, we motivate in the beginning, this is a world of new sensors, lots of sensors. And lots of sensors gave us a lot of data. And to be able to effectively process this data, we need to have big data technologies. And big data technologies face at least 3 different sets of challenges. One is the data volume is extremely large. So therefore, in that kind of setting, we need to be able to do parallel algorithms to try to do speed up. And the second challenge is, once the data is large, we face the problem of power consumption. So we have the solution of even the data instances is very large, but we need to be able to do small footprint, reducing the power consumption for the classifier. And finally, when you have this small data situation, and we can borrow supervised learning. Supervised learning can be combined with unsupervised learning. And through the transfer learning, we can improve the effectiveness of supervised learning. Okay, so let me just move into concluding remarks. To be able to build such a number of products, we started to build a cloud computing infrastructure. So this is a fundamental layer I think every company, internet company, mobile computing company has to establish. Then this IoT platform, it can accept all signals from different sensors or IoT devices. And for sure, we need to deal with the data storage indexing. And there's a viral engine in the middle, deal with sharing between devices and sharing between users. And logging, analytics, they are both critical to be able to retrieve data from the storage. But more importantly, will be this data mining component, which can get intelligence out of the data stored in the backing store. And today I show you we have launched some interesting applications, including FunFit and One Gallery and the tricorder. And based on the infrastructure, many interesting applications can be built and developed and launched in the future. So come back to the beginning of the slide. A lot of sensors are out there because of Internet of Things. And we collect lots of data. And based on the data, we apply big data algorithms to get intelligence out of the data. And that can enable killer apps to be developed. And details are listed in the references. If you are interested in learning the parallel algorithm details and the transfer learning we have just recently performed, and you can refer to these papers. And also I published a paper depicting a lot of interesting details of big data algorithms. If you are interested, you can look into. So the remaining time will open to the public for questions. Thank you.
Can you illustrate more about the transfer learning for the medical image? Like when you get 10 million irrelevant image and to do the coding, and then to extract the feature and you map the medical image using the code, using the feature you just extracted from that 10 million image, and then how do you do the classification, unsupervised or supervised learning?
Okay, so let me go back to this particular slide, right? So this just review what I just said. So on the left-hand side, you have a medical image, otitis media. And in the middle, this is a code book we trained based on this 10 million totally irrelevant data. And the training of a codebook, you can consider basically just a compression algorithm, right? Compression algorithm will give you the pivots, which can represent all your photos. And then you say, well, the photo on the left-hand side, this is not really in the training process. You didn't utilize that in training your encoding scheme. But you say, okay, how can you represent this particular new image based on the pivots here? And this is a process you can call this is a sparse coding. And you get this new vector representing the original image. And this new vector is your feature vector for that particular medical image. So you get this feature vector, and we mentioned we have 1,200 medical images. So you get 1,200 new vectors, representations, and with their labels. And you can just apply support-vector machine, whatever, onto this label data set and with the generated features. And classification can be done in that way. Right? So hopefully this is clear. Exactly. At the end, you have to use supervised learning, right? You have to have label data. But the key message here was, how did we generate this feature vector here? The feature vector generating from this process is entirely unsupervised. No physicians or experts were involved. And the middle thing, this codebook, was totally generated from non-relevant photos. None of them coming from medicine or otitis media. All of them are internet photos or the photos you took daily. And why it will work? And so I showed this heuristic about how human visual pathway works. But empirically, the next slide here basically shows, this is a paper published by Andrew Ning in ICML 209. At a high level, you can see different objects like faces, cars, elephants, and chairs. In the middle layer, you can see parts of those objects. But at the lowest layer, those are the fundamental features of all photos. So in the medicine pipeline, our trajectory right now is, from the encoding scheme, we pretty much obtain this bottom layer. So regardless whether it's otitis media or it's objects of cars or elephants, maybe our visual pathway, the V1 layer, what we have perceived, was this bottom layer anyway. So once you can get this bottom layer and you get your feature vectors, then you try to map the bottom layer to your target semantics. And otitis media could be one, and face can be another one. And because of time, or because of shutdown of the computer, I didn't illustrate all the examples, but this is the codebook we got, okay, from internet photos. And the codebook seems to be even better than the codebook introduced to us by medical experts. And the meeting slides were like, you want to identify dogs or cats. And this is an extremely challenging problem. But through the same pipeline, the accuracy could be as good as about 95%. The misclassified ones are the ones I couldn't even tell. Like, I have no idea whether this is a cat or dog. But based on the ground truth, we actually misclassify them. Right? Some of them are really tough cases. So the next one I didn't show before was to be able to classify 125 different dog breeds. Just again, based on this the pipeline, the accuracy we have achieved was close to about 80%. And the benefit of having this is, for your local or home photos, we can pretty much tell whether this is your pet or not. Because your pet would depend on, you belong to one of those 120 breeds. It's unlikely you will have photos of other pets. So once we can identify a dog and identify its breeds, then we can infer that particular dog, maybe it's your pet or not. And that can be extremely useful for tagging your home photos. Okay. So just show you a couple of missing slides before the computer shut down. And this is the system we built basically from all internet storage, from Facebook, Dropbox, and the G Drive, and Google One, HTC One Gallery, collect all the metadata, index all of them, and including the text we apply onto them. And we built this extremely powerful browsing and search engine on top. And this particular task cannot be done by Google because Facebook wouldn't allow Google to get in, and Dropbox wouldn't allow Google to access their data. But on phone, on behalf of users token, we can get into all services and aggregate metadata together and build this very powerful browsing and indexing structure. And this right now is being utilized by about 10 million people worldwide. And we are going to launch on non-HTC phones in the second half of this year.
How can I access the transfer learning paper? I saw that you just submitted.
Right. If you're interested, I can send you a copy. Just send me an email, I can send you a copy. Yeah. And I also have a tutorial on the net. Early this year, I gave a 6-hour tutorial on big data in span. There are lots of details in that particular set of tutorial slides.